Welcome to this explainer. Today, we're taking a deep dive into a really fascinating, kind of hidden molecular world. We're going to explore a topic that beautifully bridges the gap between the everyday materials we take for granted and the cutting-edge technology of tomorrow. We're talking about how a tiny, almost invisible shift in molecular structure can completely rewrite the rules of what a material can actually do. So, let's explore the hidden spark of conducting polymers.
To set the stage, think about the cables charging your devices right now. They're wrapped in plastics, right? Things like PVC. Or think about the Teflon coating on a frying pan in your kitchen. We rely on these polymeric materials specifically because they are terrible conductors of electricity. They lack free electrons, so they act as excellent insulators, keeping electric currents exactly where they belong and keeping us safe. But ask yourself, what if the exact same material we use to block electricity could somehow be engineered to actually conduct it?
Well, that what if isn't a pipe dream, it's already a reality. And the reason this matters for us is pretty remarkable. By unlocking conductivity in plastics, we basically get the best of both worlds. We get materials that conduct electricity just like metals do, but they stay as lightweight, low-cost, and moldable as everyday plastics. Honestly, these materials are the hidden architects behind some of our most advanced stuff. We're talking flexible screens you can literally fold up in your pocket, smart biosensors, and even highly targeted drug delivery systems that operate inside the human body.
Part 1. The Rule Breakers. 2 Paths to Conduction.
Now, as we established, most polymers are strictly insulators because they just don't have free electrons cruising around. But a very special class of polymers absolutely breaks these rules, reaching conductivities that rival actual metals. To pull this off, they basically take one of two paths. On one side, we have extrinsic conducting polymers. Here, the polymer is really just acting like a glue or a binder holding conductive fillers, things like carbon black or metallic fibers. You just keep adding these fillers until you hit what's called a percolation threshold. That's simply the exact concentration where those added bits finally link up to form a continuous conducting path. But then, on the other side, we have intrinsic conducting polymers, and this is where it gets super interesting. Here, the conduction is built directly into the polymer's own molecular backbone. There are no metallic fibers added at all. The plastic itself is the wire.
Part 2. The secret of alternating bonds.
So, focusing in entirely on those intrinsic conducting polymers, materials like trans-polyacetylene, polythiophene, or polyaniline, what exactly is the secret architecture that allows a simple plastic string of carbon atoms to carry an electric current? Well, the secret lies in an alternating sequence of double and single bonds along the polymer chain. In organic chemistry, we call this conjugation. Basically, each carbon atom is in an sp2 hybridized state, which leaves one valence pi electron hanging out in a pz orbital. Because of this alternating double-single pattern, these orbitals overlap across the entire backbone of the polymer. It essentially creates a continuous overlapping highway of pi electrons spanning the whole length of the molecule. The really crucial takeaway here is that this overlapping highway creates two distinct energy bands. You've got a filled valence band, which is where all the electrons are currently parked, and an empty conduction band sitting just above it. Separating them is a space called the Fermi energy gap. For the polymer to actually conduct electricity, those parked electrons need to get up into that empty conduction band. When that Fermi gap is narrow enough, a little bit of thermal or photolytic activation, so just a bit of heat or light, gives those electrons the gentle nudge they need to leap across the gap. Once they cross over, they're free to move, and bam, electricity flows.
Part 3. The Art of Doping.
But what if we want more than just a tiny trickle of electricity? What if we need a massive, useful flow? To pull that off, chemists borrow a trick straight from semiconductor technology, the art of doping. When we dope a neutral polymer, we purposefully introduce positive or negative charges. This essentially builds entirely new intermediate electronic states right in the middle of that Fermi gap we just talked about. First, it forms a state called a polaron, and then, with a bit more doping, a bipolaron. If we go back to our highway analogy, if the gap is a river with no bridge, doping basically drops stepping stones or constructs an entirely new middle lane right across it so traffic can flow effortlessly between the bands.
There are two distinct ways to build these molecular pathways. First is p-doping, or oxidative doping. This is where we use an agent, like iodine or a Lewis acid, to literally remove pi electrons from the polymer. This leaves behind a positive site, or what we call the hole in the structure. Think of it as opening up a completely empty, restriction-free lane on the highway for traffic to merge into. Conversely, we have n-doping, which is reductive doping. Here we use a reducing agent, like sodium naphthalide, to actually force an extra electron onto the polymer backbone, creating a negative site. So instead of opening an empty lane, we're basically dropping high-speed express vehicles right onto the route.
Part 4. The polyacetylene mechanism.
So how exactly does this traffic flow kick off in a specific polymer, like trans-polyacetylene? We can actually break this complex molecular mechanics down into 3 really digestible steps. Step 1. Our doping agent swoops in and either removes or adds an electron to the polymer chain. Step 2. The polymer adjusts and stabilizes that brand new charge by forming a polaron, which is just a fancy way of saying a delocalized radical ion. Step 3. A second round of oxidation or reduction happens, which forms a bipolaron. This leaves us with 2 highly mobile charge carriers on the chain, and when you place that chain in an electric field, those mobile carriers are fully responsible for the conductance.
Let's look at this actually happening. This is the oxidative p-doping mechanism of polyacetylene using iodide. In that first reaction, the iodine comes in and snatches an electron away from the chain. That creates our radical cation, the polaron. Stripping away those pi electrons leaves a literal hole between the valence and conducting band. Then a second oxidation hits, yielding the bipolaron. And just like that, we have mobile, positive charge carriers zipping across that conjugated highway.
And right here is the exact mirror image of that process, N-doping. In this case, sodium naphthalide is acting as our reducing agent. It donates an electron to the polymer chain to form our polaron, which is now a radical anion. If you trace the path, notice how that added electron settles right into that intermediate energy state within the band gap. One more reduction step forms the bipolaron, giving us 2 highly mobile negative charge carriers ready to conduct.
Part 5. Powering our world.
We've zoomed pretty far down into the microscopic weeds to understand the bonds, the energy gaps, and the electrons. But what do all these polarons and bipolarons actually do for us in the real world? Well, because these intrinsic conducting polymers are light, highly moldable, and conductive, they are actively replacing heavy corrosive metals across modern engineering. They're being used to build small, high-current density rechargeable batteries. They're at the heart of analytical biosensors detecting things like glucose, pH, and oxygen levels. Because they have this amazing selective permeability, they act as ion exchange membranes to control the precise release of drugs in the human body. They light up electronic displays and LEDs, and they even help us capture the sun's energy in advanced photovoltaic solar devices.
It's honestly incredible to realize that the exact same basic material we use to coat a wire to stop electricity can, with just a pattern of alternating bonds and a little bit of doping, become the very thing powering our most advanced technologies. Literally, a simple molecular tweak transforms an everyday, boring insulator into a powerful conductor. So the next time you pick up a smart device, maybe ask yourself what other insulators in our world, whether they're materials or something else entirely, are just one small structural shift away from unlocking some incredible hidden power. Thank you so much for joining me on this explainer, and I will see you next time.